Hello and welcome to today's class. This is the second of two videos looking at optimization. In the first video, we looked at optimization and the impact that it can have on the design cycle in terms of time and cost when you're developing products. In today's class, we're going to look in a bit more detail at what optimization is, the theory behind it, the techniques which are used, and some of the pitfalls that you can come across when you're doing some optimization. We're also going to have a look at a couple of mathematical examples, simple mathematical examples using optimization. And then finally, we're going to look at the different sorts of optimization that you might come across: topology, topography, and so on. So in the last video, we were talking about optimization and the impact that it can have on the design process. In today's class, let's actually consider what's going on there. So what is optimization? Okay, so first of all, a dictionary definition: the greatest degree or best result obtained or obtainable under specific conditions. So generally, when we optimize something, we need variables, objectives, and constraints. So something that we can change, something that we're trying to do, and something which is constraining our problem. So we have an initial design, we analyze it, we do some numerical calculations, maybe we understand how that model is performing, and then we evaluate that. And then we need to make a decision. Has the optimum been achieved? Well, if it has, then yes, there's our optimum design. If no, then we go back to the drawing board, change our variables, go back into here and reanalyze it. Okay, so we go round and around in this loop. Okay, so what I was talking about last time, in terms of a CAD-led concept, this part here traditionally has been done by people using gut instinct, using experience and judgment. So they'll evaluate a design and then they'll decide whether or not they can change something, and then they'll re-evaluate it. And so this part here is done iteratively. What optimization does in this context that we're talking about today, this section here is now being automated. We're starting to integrate that into our finite element analysis software or whatever we're doing. So we're starting to automate that. So let's have a look at how we can do that today. Okay, so what are our variables? Well, our variables may be things like material properties, package space, where we would put material. When we do that, we need to think about what material is designable and what material is non-designable. So there'll be certain points which are non-designable, for example, where, I don't know, seat belts attach or roll cages attach or something like that. We've got certain hard points that we cannot change. However, there's going to be certain points which we can change, certain material where we can influence what's going on. We only put that material there if it's needed. So that's our designable material. Other variables might be panel thickness. If we're looking at a fabricated structure, how thick are our panels? Or if we're looking at a composite, we might talk about the laminate layup, how many plies we lay up, the orientation of those plies, the stacking sequence, and so on. Okay, so any of these can be our variables, something along those lines. And they can be discrete or continuous. So when we're talking about discrete variables, they could be, for example, if we're talking about a laminate layup, we can have 1 ply, or we can have 2 plies or 3 plies, but we can't have 1.5 plies or 2.5 plies. Okay, so there are certain discrete values which we must choose, and those are generally dictated by the manufacturing constraints of our model. Or we could have continuous variables. For example, if we're talking about the thickness of a casting, then that can be any value, generally between our minimum value and our maximum value. So our minimum value might be dictated by our manufacturing constraints, by filling the die. Our maximum value might be dictated by our manufacturing constraints in terms of porosity and that sort of thing. But between those two values, those minimums and maximums, we can have any value pretty much between those two values there. So our variables can be discrete or continuous, and we would look at something like that when we need to think about our manufacturability at that point when we're discussing our variables. Our objectives, well, it must be a measurable response. If we're trying to automate what's going on, we need to evaluate the structure. So we must be able to measure the response. And generally, we will try to minimize or to maximize that. So we might be trying to, I don't know, minimize mass or maximize frequency or minimize displacement or minimize stress or minimize strain. We need to minimize or maximize one of those things. And that gives us a clue as to what we're actually going to do here. One of the techniques used for optimization is gradient-based optimization, because we're trying to minimize or maximize our response. And our response our objective can be, we can have multiple objectives. We could be looking to maximize mass, minimize mass and maximize, or minimize mass and minimize displacement, for example. Or we might only have one objective, which is to minimize mass, for example. And lastly, we need constraints. We need all of those three things. We need variables, objectives, constraints. So our constraints might be only to use 30% of the material, or to limit deflection to a certain amount, or a certain mode must be above a certain frequency, for example, which would tie in with an OEM's modal alignment chart, where they try to have certain components within a assembly or sub-assembly to make sure that they don't align, they don't excite each other. Or we might have a limit on strain for a certain material. For example, I was talking about a magnesium supply that I was working for, and the maximum strain that we could see was something like 7%. Beyond that, we would see failure. So we must have those three things: variables, objectives, constraints. If we don't have one of those three things, we can't optimize the structure. For example, if our variable is the material and our objective is to make it as stiff as possible, if we don't have a constraint, then the answer is quite obvious: just use all of the material. You have your variable is the material, you've minimized displacement by using all of that material. However, that's nonsensical. Our constraint only to use 30% of the material, for example, suddenly forces us to come up with an optimum design to tell us where the material needs to be, which material is of most importance and which material can be removed, which material is of less importance. So we have variables, objectives, constraints, and we can have feasible and infeasible solutions. So it's possible that we could set an impossible task if we want to, let's say, our variable is our material, and we have a displacement constraint on there. That may be impossible with the variables that we've got. There's no way, we can't. The laws of physics still apply. Our structure can only have a certain stiffness with that amount of material. It may be that we can't meet that displacement constraint. So we need to be aware of that. And generally, when we're optimizing something, there will be limits placed on that in terms of the number of cycles, in case we have set the software an impossible task, so it doesn't carry on iterating forever, ever. It will go so far and say, well, actually, I can't meet this constraint that you've set me, and therefore the job is going to terminate, to make sure that we don't see the software computing indefinitely. So one way to achieve optimization is by considering the gradient of the thing which you are measuring. So gradient-based optimization. As I said in the previous slides, we are trying to minimize or maximize that objective. So if we can plot our response and then work out the gradient of that response, we can work out whether or not we have reached that minimum. Okay, so our responses are generally shown either to be convex, so that is we've got one minimum, or quadratic, so or non-convex rather, where we have multiple minimums. If we've got a convex function, the local minimum is the same as the global minimum. Okay, so that's relatively easy to solve. However, a lot of the time we end up with a non-convex function where we have a local minimum, but we also have a global minimum. And there we can see our global minimum is lower than our local minimum. So we might end up finding this local minimum. So when we optimize our structure, we think we've got to the bottom of our function, and we have locally. However, there is a better solution down here, a global minimum. So a minimum, it cannot, a local minimum may not be the global minimum. A minimum can only be guaranteed if the problem is a convex problem. Okay. But a lot of the time, most engineering problems can be shown to be non-convex. So we end up with this scenario. So we've got our function, which we're plotting. We're calculating the gradient of that function as we iterate our problem. However, we might find a local minimum rather than a global minimum. For example, if we were to, and that depends on where we start. For example, if we were to start at position A here and iterate our problem, by the time we get to position P, we think we've found the optimum solution. But what we've actually found is a local minimum, not the global minimum. If we were to start at position B, we would find the same local minimum. We'd iterate our structure, we'd end up down here again. We've got a local minimum. However, if our starting point was up here and we were to iterate our structure, when we find a minimum, that's minimum there, is actually the global minimum. Okay, so whether we find a local minimum or a global minimum clearly depends on where we start. So one way to get around that essentially is by using a scattergun approach, by having multiple starting points. So that obviously has a computational cost because rather than just having one model, which we're iterating, suddenly we need several models with different starting positions. We change our variables, we start in different places, we iterate those, and then we come up with the optimum solution and we choose the one which is best. And we assume, therefore, that that is a global minimum. But that, like I say, cannot be guaranteed. So this is essentially what's going on. Our gradient descent method. So we start at this point here, we iterate our structure, we measure the response, the gradient of that response. If that gradient is still heading down, if we're looking for a minimum, or heading up if we're looking for a maximum, we carry on to our next iteration until the gradient is 0. And then at that point, we have met our minimum or our maximum. Okay, so it's an iterative solver. We're repeatedly analysing our structure, and we need to bear that in mind when we build our FE model. If we were to optimise that, the computational cost is actually quite high. So a model might only take a couple of minutes to run once, but if we come to optimize that, that is going to have to run several times, and the computational cost and the hardware and the software needed to do that is quite significant. So we will converge, hopefully, on a local minimum or ideally on a global minimum. So there's different sorts of convergence which we can have. We can have regular, some software called it regular convergence or hard convergence. So the convergence criteria is satisfied for 2 consecutive iterations, or the constraint violations are less than a certain tolerance. So we might say from one iteration to the next, if they're within a certain tolerance, then we stop. We've met our our minimum or our maximum, we've converged on a solution. Or we might have soft convergence. And what do we mean by soft convergence? There's little or no change in the design variable for 2 iterations. There's very little change from one iteration to the next. So the software decides, actually, I might as well stop iterating. There's your final solution. So you want to optimize a structure. You've set up your variables, your objectives and your constraints. And then you try and solve your model, and then for some reason it won't solve. So what are potentially the issues? What could potentially be going on? Okay, so here are some general pitfalls which you might find in optimization runs. For example, the problem could be unbounded. And what do I mean by that, an unbounded problem? So for example, if you're trying to minimize volume with a stress constraint only, the solution is quite obvious: have no material, therefore you've got no stress. Again, that's a nonsensical solution, but that is quite logical. If you're trying to minimize stress, just get rid of all of the material, therefore you have no stress. How would you get around that? You need to add a constraint, add a displacement constraint. For example, clearly if you've got no material, your displacement would be infinite. So put a constraint on that, and therefore that solution is no longer valid. You could have an over-constrained problem. So your constraint of compliance and constraint on mass, not possible with the given variables. So you've over-constrained your problem. You've asked the software to do something impossible. You put too many constraints on it with the variables that you've got. That's not possible. So what would you need to do? You need to change your constraints. So for example, if you've put a displacement constraint on the structure with certain variables and it's not possible to meet that displacement constraints with those variables, then potentially one way to get around that would be to change the constraints to make it less restrictive. You could have a manifold solution where there are multiple modes for the same response. For example, when you're looking at buckling of struts, you could have the fundamental buckling mode where you've got a half sine wave as the strut buckles, but actually the force needed to buckle that structure would be exactly the same if you had 2 sine waves or 3 sine waves as that strut buckles. So there are multiple solutions. And so that would not converge. So one way to get around that would be to add constraints to a particular mode to force the software to choose a particular mode shape. You could have a problem with no solution. For example, to minimize stress. Let's say in your FE model, you're applying a force at a point. Stress is force over area. If you're applying a force at a point, your stress, in theory, is infinite. If you're trying to minimize the stress and there's infinite stress in your model, then clearly that's not going to converge. One way to get around that would simply to be exclude that region from the constraint. Where you're applying that force, exclude that from the part that you're measuring, and so therefore you're not going to measure that infinite stress. Finally, the last problem on here, the last pitfall you could potentially come across are where your variables are at their minimum or their maximum. So for example, again, you've set an impossible task. Let's say you've put a displacement constraint on something and you've said your variables can change up to a certain value. They've gone to their maximum. They're still not meeting your displacement constraint. Earlier we said, well, therefore change your constraint. Alternatively, you could obviously change the bounds of your variables. You could increase the thickness of the panels, for example, so that it's now possible to meet that constraint. Okay, so let's look at a simple mathematical example. Let's say you're working for a manufacturer which produces containers and they want to optimize their structure to ensure that their customers can put as much product into their containers as possible, but they only want to use as little material to make those containers as possible. So our objective might be to maximize the volume. Our constraint only use 2 square meters of the material, and our variables are H and A. Okay, so the height of the container, the breadth and depth of the container. We only want to use 2 square meters of material, and we want to maximize the volume so that our customers can put as much of their product inside our containers as possible. So we've got objectives, we've got constraints, and we've got variables. So let's have a look at how we would go about solving that. So I'll put this PDF onto Teams for you so that you can see how we would go about solving that. Here we've got that problem. So what is H and A such that the volume V is a maximum? So that's our objective. The area A is 2 square meters. That's our constraint, and our variables are A and H. Okay, so the first thing that we can do is we can write down our objective in terms of our variables. So our objective volume equals A squared times by H, simple geometry, A squared, so this area here, times by the height, that's clearly the volume. So there we've got our objective written in terms of our variables. The next thing that we can do is we can write down our constraint in terms of our variables. Now our constraint is the surface area. So our area equals A squared, that's the bottom, plus A times by H, they're the sides, and there's 4 of those. We've got no lid on our container, so there's no third term there, which would be our lid. So there's the base of our container, and then 4 sides of our container. If we now rearrange that in terms of one of our variables, H, we can then put that into our first equation here, where we write down our objective in terms of those variables. So instead of having 2 variables there, we're only going to have 1. Okay, so let's put equation 2, this one here, into equation 1 here. So we've got that there. And then clearly we can divide 3 by A, divide 3 by A. So there we've got our objective in terms of one of our variables, A squared. So there's our objective, and there's our variable A, and we can have some sort of function. We've assumed we've got a convex function there, an inverse convex function, and we want to know what value of A will give us our maximum volume. Okay, so let's rewrite that. I've just swapped X with A there, so that when we come to differentiate it, we're working with X, which we're more comfortable with potentially. So this equation here, I've rewritten that there, but I've rewritten it with X instead of small a. Okay, so there's our objective, and there's our variable X. We expand that, we get that term there. Okay, now if we want to find a maximum, we know that if we were to differentiate that and equate that to 0, at that point, that would be our maximum. Okay, we know we've only got 1 maximum, so our global maximum is the same as our local maximum. We're only going to come across 1 maximum here. Okay, so let's take that function there and let's differentiate it. So ax over 4 becomes a over 4, x cubed over 4 becomes 3x squared over 4. Okay, so we've differentiated it with respect to x, and we've said it's equal to 0. So there we go. So let's rearrange that. So x equals plus or minus the square root of a over 3. Now a, remember, is our surface area, and we set that to 2 square meters. 2 square meters here. Okay, so x, our variable, equals plus or minus the square root of 2/3, which equals plus or minus 0.816. And here we've got the scenario where there's 2 solutions, but actually obviously one of them is nonsense. We can't have a negative depth there. Remember x, which we switched for a here, which is this here. Obviously that distance there can't be a negative number. It must be a positive number. Okay, so obviously the solution must be positive. So it's 0.816 meters. Okay, if we then put that variable back into here, we can work out what our objective is. And our objective is 0.2 0.272 meters squared. So when our variable, our base is 0.816 by 0.816, the volume inside the container would be 0.272 meters cubed. And then once we've got one of our variables, we can work out what the other variable is. So let's put that variable into here. We know now what our objective is. We can put our known variable into there. We can work out what the other variable is. So it's going to be 0.409 meters high. So there we've got a really simple example showing how we can calculate this variable and this variable, which is the same, and this variable, our second variable. So let's look at those two variables, work out what they are to maximize the volume inside our container with the constraint of only using 2 square meters of material for our container. Okay, so let's look at some different sorts of optimization that you may want to do. So the first sort of optimization that you may come across is topology optimization, and this has seen an awful lot of interest over the last few years because of contemporary manufacturing techniques such as 3D printing, additive manufacturing techniques. So the big downfall for this in the past was getting from a sort of organic design that these sorts of this sort of topology optimization comes up with, and interpreting that into a manufacturable solution. But actually now that's much easier because of, say, contemporary manufacturing techniques such as additive manufacturing. So here we've got a motorcycle swing arm or something like that. We've got designable regions and non-designable regions. So our non-designable regions would be these grey circular parts here where we're attaching to the frame or the swing arm or whatever. And then we need to understand our package volume, and we've got our designable region there shown in yellow, shown in gold. So we want to understand where we would put the material in order to minimize the amount of material. We only use 30% of the material, for example, to join those 3 non-designable points. So we would use that in early conceptual design stages in order to understand what the major load paths are. So we've got our geometry, we apply our loads and our constraints, and then we might look at manufacturing constraints on there as well. So for example, if we want it to be symmetrical, and then we optimize our solution, we come up with that solution, and like I say, then we would then need to interpret that into a manufacturable solution. Okay, so you can see clearly we've identified those major load paths through our optimization run, and there you can see how we've interpreted those into a final design. But actually this step here is not as hard as it used to be because of contemporary manufacturing techniques such as 3D printing, for example. When we're thinking about our topology optimization, we think about our designable regions, our non-designable regions. We add our boundary conditions and our load cases. We need always to think about variables, our objectives and our constraints. Our variable might be the amount of, the material itself. Where is that material? The objective might be to minimize compliance or maximize stiffness. And our constraint might be, for example, only to use a certain percentage of the material, 30% of the material, for example, 5% of the material, or whatever. One thing to note here is that this sort of optimization defines major load paths. So if the material is linear, the material choice is irrelevant, actually. It wouldn't matter if you were looking at this as an aluminium billet or a steel billet or a titanium billet. The major load paths would be exactly the same. What the structure here, what the software is doing here is identifying those major load paths, and we need to ensure that those are integrated into our design. So this enables us to understand the material usage. We might put on there minimum member size, We'll come on to that in a minute, I think, when we talk about what minimum member size does. It forces a structure to have a minimum member size. The example I always give, if you think of a bicycle wheel, the minimum, the members are very thin, the spokes leads to a very efficient structure with not much material at all, but clearly that forces a manufacturing technique. Clearly you wouldn't be able to cast that, for example. You need to assemble that structure with those spokes. We would put a spread fraction on there to ensure that our load paths are spread out. We might put manufacturing constraints on there, such as these, if we're looking to extrude the structure or stamp the structure, or we might put symmetry constraints. So our structure might be symmetrical for aesthetic reasons or for other reasons, or we might have cyclic symmetry, for example. So we can take all of these things here and put those onto our variables to drive our design. In terms of how much material we would use, try 0.3%, 0.3 to start with, so 30%. It generally gives reasonable results. You might need to try playing around with that value. For example, in a minute, we're going to look at a roll cage in a vehicle, and the material usage was much smaller than that because of the sheer volume that we're starting with. But as a first stab, as a first guess, it's reasonable to say, okay, let's look at 30% and take it from there. You might need to try and play around with that value. Our minimum member size controls the smallest dimension to be retained. I gave you the example of a bicycle wheel a minute ago. It also forces 0 or 1 answers to stop this sort of thing happening. This is known as checkerboarding. So without the minimum member size here, you can see this structure. We've got lots of non-0 or 1 answers. The minimum member size is going to force that. So we see a much cleaner result there. Okay, so our minimum member size will force those values there. As a tip, try 3 times your element size to start with. Clearly, your minimum member size is going to be dependent on your element size. So with much smaller elements, you get a cleaner solution. With much larger elements, you might find that the load paths or the structures that are being suggested are influenced by the elements which you're using. Here's an example. We've got a simple cantilever beam here. So we've been constrained at one end, being held at one end, a load applied at the other end. Here we've got the structure, our topology result, and our interpretation of our topology result with one load case. Here we've got it with multiple load cases, and actually, you can see clearly the difference here. Here, I think we're loading it downwards. Here, we're loading it sideways as well, and also in the middle here. And you can see, you might be able to guess this sort of structure with a package volume and one load case. It's quite a simple solution, but as soon as you start looking at multiple load cases, that is not obvious what that solution would be. So here you can see we're loading this structure downwards in the center here. So we've got this member coming down here, this member coming down here. We're also loading it downwards at the end here and sideways at the end here and sideways at the end here. So we've got quite different, a non-obvious structure. There you can see there's our organic structure without any manufacturing constraints. That in theory would work, but would be very difficult, for example, to cast. So here you can see a similar or the same structure, but optimized with manufacturing constraints this time. So here we're saying, okay, we want to cast this structure. So clearly we couldn't cast this. We could cast this sort of structure. So you can see the influence of the manufacturing constraints on your topology run there. Alternatively, you might have something like this. So here we've got a structure where the A surface, this square surface here, is already defined. But what we don't understand is how we would reinforce that, the ribbing which would go in the back of that. So here we've got our A surface, we've filled the back with solid elements. That is our variable, and then we've taken our result, our topology result, we've interpreted that here. Look, there's our interpretation, and that is clearly being driven by the optimization run. So the optimization is being used to drive the design, to understand where our major load paths are, to tell us where we need to put material to ensure that we meet those major load paths. Finally, here's another example, something else that I've worked on. So here we've got a structure, a mini. We need to take that structure and we want to put a roll cage in there, for example. So a very early structure, a very early study would be to take that package volume, subtract certain material where we can't have members. So for example, the window, the engine bay or the passenger bay. Let's take that, let's load that via torsion or bending or whatever we're interested in, and understand where we need to place material in order to minimize displacement in those load cases, for example. And there's our result, and we would take that result and we would then interpret that into our roll cage, so we can understand there where we've got members. That's going to tell us where we need to place tubes in our roll cage, and then we would then move on and look at another sort of optimization where we'd look at sizing the tubes, the tube diameter or the tube thickness. So the next sort of optimization that you might come across is something called topography optimization. So here, this is typically used to put a swage pattern or bead pattern on top of a thin structure. So here we've got a tank with internal pressure. It might look like something like this originally. So our objective is to make it as, or to minimize the deflection, how much this tank deforms when it's pressurized. So initially it might look something like this, and the traditional approach might be to say, okay, well, let's put some more reinforcements in there. Let's reduce these flat areas. So you end up with something like this. So our deflection has actually got worse. We've gone from 10.8 mil to 13.9 mil. But actually the solution should look something like this. So here you can see we've used optimization software and we're actually minimizing our deflection. This is a non-obvious solution. So looking at something like this or looking at something like this might be sort of a more iterative approach based on judgment and experience, but actually the optimum solution is far from obvious. Here you can see we've used some optimization software to minimize the deflection there, okay, to understand where we would put the swages on there. So how would we do that? Well, our design variable this time is obviously this flat surface, how far away from that plane the nodes would sit on that flat surface. So we need to think about the position of those nodes relative to that plane. And we also need to think of the manufacturing constraints. What would be our maximum bead height? What would be the draw angle? What would be the maximum bead width due to the fact that we're stamping this out of our flat material. So our variables would be the position of the nodes on here. Our objective in this particular example was to minimize displacement, and our constraints would be driven by our manufacturing process in terms of the bead width, draw angle, maximum bead height, and that sort of thing. So here's another example. Here we've got a model where we're trying to increase the natural frequency, the first mode of that structure. So we've got an oil pan. We're trying to understand how we would change the position of the nodes on that flat surface to maximize the frequency of that first mode. And here you can see the optimization run, the position of those nodes, shown there, and there you can see we've interpreted that into a design, a non-obvious design. So without beads, this thing vibrates at 619 Hertz. The ideal solution there is now vibrating at 1551 Hertz. But actually, when you turn that into a manufacturable design and you actually come up with something, you simplify, you interpret it, you'll see a slight reduction. It's not as efficient as this. This is the ideal solution, but this one you can actually manufacture. But you can see there's still great benefit from doing that. We've gone from 619 Hertz up to 1422 Hertz in this example here. So next we come on to size optimization. So earlier we saw how you might use topology optimization to understand your major load paths where you need to put material. You can then use something called size optimization to change the physical property of the elements that you're dealing with to understand how you would change those physical properties to give you the optimum solution. So for example, you might use it for shell thickness if you're using two-dimensional elements, or you might use it for tube thicknesses or tube diameters when you're dealing with one-dimensional elements. So here's another example. Here we've got it looks like a bicycle frame. Clearly we've done some sort of topology optimization there. We've come up with that solution there. We've identified where our major load paths are. We now want to take that and put a one-dimensional element on there, our tubes, but we want to use size optimization to understand the tube diameters and the tube thicknesses, how we would actually manufacture this. When we do that, these variables could be real or they could be discrete. So real variables, for example, we might say the tube diameter is between a certain value and a certain value, a minimum and a maximum, or we might have discrete values. We might look at our suppliers and say, well, actually, they only offer these certain diameter tubes or these certain thicknesses of tubes. So therefore, we want to force those discrete values so that we end up with something which we can actually manufacture. So here's an example where we would optimize a structure such as this. So here's a bicycle frame. We've got some constraints on there. We can see the rear dropouts here, and on the headstock there, we've got some forces on the crank, forces on the saddle, and so on. And you can see we're optimizing. Here are our variables now. Our dimension 1, which is our tube radius for the outside dimension. Dimension 2, which is the tube radius for the inside dimension. So if we change those two variables, clearly we can work out the tube diameters or the tube radiuses and also the tube thicknesses. We optimize that structure so that we can work out what tube diameters and tube thicknesses we would need. So on the previous slide, we were talking about size optimization, where you are changing the physical property associated with an element or an element group. The next sort of optimization is called free size, or some software companies call it topometry optimization, where rather than changing the physical property for the entire set of elements within a group, you're actually changing each of the thicknesses for each individual element. So that can be particularly advantageous when you're dealing with a structure where you can have local thicknesses introduced into a structure. For example, if you're casting a structure, obviously you don't need to increase the thickness of the entire component or the entire surface. You could, for example, have local increases in thickness just where you need them. So topometry optimization. Next, we have shape optimization. Shape optimization enables you to understand the shape of the structure, how you would change the geometry of the structure in order to minimize or maximize a response. That requires you to have knowledge of the kind of shape you would like to change. For example, in a structure where we've got a tube joining onto an extrusion such as this, we can see here, we might say, okay, well, what radius would we need? How would we join that tube? What fillet would we need to put in there, for example? Or so we might see something like this. So what is the what is the shape of that tube as it comes in there? Or, for example, a bead in a bracket. So, for example, we might have a bracket here, it's loaded in some ways, it's constrained here in these three holes that we're applying a load here. We need to understand what bead we would put in that bracket in order to minimize displacement, for example. So we might look at the structure like that and then understand, okay, well, there's our shape of our bead, which needs to go in there in order to minimize that displacement. Okay, and the last sort of optimization that I want to go through today is composite optimization. Now, composite materials are problematic in that they have different material properties in different directions. And if we don't know what we're doing, that makes designing components out of composites very, very difficult compared to an isotropic material such as a steel or an aluminium, which has generally the same material properties in all directions. But composite materials, when we've got a structure made up of two or more constituent parts, we need to understand how we would combine those elements to give us the response that we need. If we use optimization, that gives us a great deal of opportunity to optimize the structure so it's as light and as stiff as possible, if that's what we want. So we only have stiffness in the directions where we need it. And where we don't need stiffness, let's remove material. So let's take advantage of those non-isotropic material properties so that we can optimize our structures and make them much more efficient. And we're starting to see that with aircraft and cars and sports equipment, civil engineering and so on. So let's use optimization to change. These are our variables now, our fibre orientation, the number of plies and the stacking sequence, for example. If we look at our material properties, clearly we've got E1, so this is the stiffness in the fibre direction. And here we've got E2, the stiffness in the lateral direction, so perpendicular to the fibre. So this would be potentially a unidirectional composite where the stiffness in the fibre direction is much greater than the stiffness at 90 degrees to that. So this stiffness here would be driven by the fibres, and this stiffness here would be driven by the epoxy or the matrix. If we're talking about a fibre reinforced plastic, this would be dictated by the plastic, if you like. So it's important to understand that, that we've got different material properties in different directions, and you may come across an anisotropic material or an orthotropic material, and it's important to understand the difference between those two different materials. An anisotropic material has got different material properties in different directions, whereas an orthotropic material has three mutually perpendicular material properties in X, Y, and Z, typically, or X and Y and out of plane. So we can use optimization in order to optimize a composite structure to tell us where we would need plies and the orientation of those plies. Something which is important to understand when we do that is something called zone-based modelling. So if we consider a composite structure, here's a cross-section of a composite structure. We've got some sort of structure here. We've got a rib here. Okay, here we've got our skin outer on here, and it goes into flange, what's called flange 1, this region here, this zone here, flange 1, this zone here, flange 2, this zone here, our skin outer. Okay, if we consider this region here, we've got 5 plies, and we can see ply number 3 comes along here and stops at this location. So ply number 3 here is this red ply here. But in the skin outer, ply number 3 is not the same structure at all. Ply number 3, if we follow that across here, is ply number 5 at the skin outer. So at the skin outer, it's ply number 5, and here at this end, the skin outer is now ply number 3. But actually, that's the same ply. So when we come to look at our responses, let's say, for example, we're plotting stress on ply number 3. Ply number 3 here is not the same ply as ply number 3 in this region here. It's in a different zone, and because of the manufacturing technique, ply number 3 stops at this point here. So if we were to plot ply number 3 over here, clearly that's a different piece of material. Okay, so just something to be aware of when you're optimizing a composite structure. Have your plies changed because of your manufacturing process. So they're the basic optimization techniques which we've talked about today: topology optimization, topography optimization, free size optimization, or size optimization first, and then free size and topometry optimization. Shape or free shape optimization, so this idea of changing the geometry. Composite optimization, which we've just talked about. What's going to happen next? I don't know. There's scope to optimize our structure using other techniques, I'm sure. But all of those techniques use the basics of variables, objectives, and constraints, which we talked about at the start of today's class. So today's notes have been taken from this book by Altair. A lot of the images are from this book by Altair, and I recommend you read that. So practical aspects of structural optimization. It's on the Altair University website and part of the recommended reading list for this course. So today we've been talking about optimization and looking at the theory of optimization and some of the shortfalls of optimization, why your models might not work, and the different sorts of optimization techniques that you may come across. Like I say, today's class is one of 2 videos. Please watch that first video if you haven't watched that already. What I will do, I will upload to the Teams area the PDF associated with the notes, or with this video that I've just been through. I'll also upload that mathematical example that we went through earlier, that square container, where we optimize the size of that container, the height and the width. I'll also upload another mathematical example, which is quite similar, but this time a cylindrical container, and we're optimizing the radius and the height of that container to maximize volume. So have a look at those and have a look at those in conjunction with what we've been discussing in today's class. And until next time, I will see you then. Okay, cheers, bye-bye.